This is the fifth lecture in Chapter 13, Kinetics. We have talked about relative rates of disappearance and or appearance of reactants and products. We have talked about differential rate laws and then moved into integrated rate laws. And then finally talked about the kinetics of radioactive elements, because they are all first order. And so now we're going to talk a little bit more about the theory of the things that affect the rate of reaction, and then we'll be shown a formula that shows you, even though we call rate little k rate constant a constant, it can change with temperature. So I think I've mentioned at the beginning of the chapter about collision theory, but that simply says that in order for a reaction to occur, collisions have to occur between the reactants. And that anything that increases the frequency of collisions will increase the rate of reaction. So what are the types of things that will affect the frequency of collisions? Temperature, okay? So obviously the more temperature, or the more you raise the temperature, the more kinetic energy you give the reactants, and therefore they are going to collide not only more frequently, but when they do collide, they're going to collide with more energy. And we're going to be talking about something called activation energy in this lecture, and you'll see that colliding with enough energy is very important. We will also see how the concentration, well, we already have seen how the concentration can affect the rate of a reaction. You particularly see that in the regular rate law, differentiated rate law. Concentration is an important factor. And in this lecture, we'll talk a bit more about the importance of surface area available for collision and contact, as well as how a catalyst and an inhibitor can affect the rate of a reaction. This is just kind of writing out in a bit more detail. What I said in the introduction slide is that molecules must collide in order for a reaction to take place. And this PowerPoint focuses somewhat on what we call activation energy, and that is the energy that reactants need in order to actually produce a reaction. So, in other words, reactants can collide, but if they don't collide with the proper energy, there won't be a chemical reaction. Reactants also must collide in the proper orientation, right? So, if we have, I'm just going to make up a molecule. If we have a molecule that has a spherical shape on one end and a cubic shape on the other end, and let's say we have two of these molecules, and in order to react, the cube end of it has to contact each other, okay? So if that's the case, if that's the orientation you need for a reaction, then any other orientation, no matter how much energy they collide with, is not going to give a reaction. So in this make-believe molecule, if they collided spherical side to spherical side, there's no reaction, or spherical side to cubic side, there's no reaction. So activation energy, again, is the energy, the minimum energy required for a reaction to occur. So regardless of whether a reaction is endothermic or exothermic, all reactions need a certain amount of minimum energy to get going. It's kind of a kickstart. And part of that activation energy, if not most of it, is the energy required to break bonds. Now, they're not equal to each other, but that's a good part of it. All right, so now this particular example is an exothermic reaction. How do we know that? Well, it's important. If you're fuzzy on that, go back and review it carefully. It's very important. Exothermic because the products are lower in energy than the reactants. So the system has gone down in energy, which is a good thing. Remember, in nature, we like to go to lower points of energy. It's more stable. But all of this extra energy was released to the surroundings. Okay, so that's exothermic. Okay, but the fact that it's exothermic has nothing to do with the activation energy. So even if it's an endothermic reaction, where the products are higher energy than the reactants, you still have the activation energy. And so notice that activation energy is the energy difference between the reactants and the highest energy point on the reaction profile. So this highest point is referred to activated complex or transition state, which is not something you're going to use much now, but just to let you know. All right, so again, just to give you a visual, the collision theory says reactants have to collide in order to react, but any old collision is not good, okay? So let's look at how these two reactants react with one another. You can see that the green spheres, which are representing chlorine, by the way, are going to end up bonded together. So these should collide in proximity to one another, right? So that they can make a bond. So if they collide so that the green spheres, the chlorines, are away from each other, it's an ineffective collision. There's going to be no reaction, right? So there are several different wrong ways it can collide, and only when it collides with the correct orientation, which in this case, and again, you've got to look at what's making a new bond. In this case, the two chlorines, and that is perfect orientation. So to summarize, an effective collision, one that results in a chemical reaction, is a collision that has enough energy to surpass the activation energy and also has the correct orientation so that a new bond can be made. So these are the two key properties of a collision that need to be met. Now, I introduced in the title slide the factors that affect rate of reaction, and so we're going to go over them a bit more detail here. So temperature is one of the more important ones. The temperature, this is the most important piece of information to get out of this slide. Temperature results in more frequent collisions, right? Because if the kinetic energy of all the particles is higher, it's like putting a bunch of kids in a room, shutting the door and tell them to run faster and faster and faster, okay? So you're going to have more frequent collisions, but also the collisions that you do have are going to have higher energy. So there's a more probability at a higher temperature and higher energy collisions that more molecules are going to achieve this activation energy. They're going to be able to get over the hump there to make products. And in addition, the rate constant, which we'll focus on a bit later in the PowerPoint, is temperature dependent. Even though we call it a constant, it's constant unless you mess with temperature. So here's the actual formula for rate constant that shows you it's not exactly a constant. Okay, so as temperature goes up, rate constant will go up. That may seem counterintuitive, but notice that the exponent here is negative. So as temperature goes up, this whole exponent becomes less negative, and rate constant goes up. And then activation, you can see there is, in fact, a relationship between activation energy and rate constant. All right, so as the activation energy goes up, okay, that means a higher hill. So there's activation energy for some reaction. And let's now do this. Okay, so the activation energy, again, it's a difference in energy between the reactants and the highest energy point on the reaction profile. The activation energy in the bottom one is higher, and the higher the activation energy is, the lower the rate constant is. Okay, it makes sense. If you make a higher mountain, it's going to be less frequency of molecules able to make it achieve that energy and make it over the hill. The rest of the factors, I mean, temperature has to be in Kelvin if you use this. This is the universal gas constant, which manages to show up every place. And since we have energy in this equation, in this formula, now remember, energy, the units we most commonly use are joules, right? Joules or calories, but joules is what we've normally used. And so anytime, remember, you want to match the units of the gas constant to the units of whatever other variables are in the formula. And since we do have energy, we would want to use the R value of 8.314 joules per mole Kelvin. This is a type of graph interpretation that you need to get comfortable with, and it presents somewhat of a struggle to students. So I want you to spend a good several minutes on it, make absolutely sure you understand it. So on the y-axis, look carefully, it is not energy like you're used to, right? Energy's down here. Okay, so higher energy is this way. And I think that might be why it presents a struggle to a lot of students. The y-axis is kind of odd. It's the fraction of molecules. So if you have 100 molecules and 50 of them have enough activation energy to make it over this hill, right? Then you would say the fraction would be 1/2, right? 1/2 have enough energy. So that's what fraction means. So and energy is increasing going to the right. So let's say I gave you the activation energy. I said, okay, the activation energy for this reaction is, well, I'm just making up values, 1 times 10 to the 5th. And so you would mark that energy on your x-axis. Remember, energy's in the x-axis. We're used to being on the y. And you would say, okay, in order for this reaction to occur, the molecules had to have at least this much energy when they collide. All the molecules that have less than that energy will not react. All the molecules that have at least the activation energy or more will react. Okay, so what are the difference between the blue outline and the red outline? The temperature of the red line is higher. That makes sense, right? If you increase temperature, you increase energy, kinetic energy. Just think kinetic energy, right? Okay, so the curve does flatten out more, so you get a wider range of kinetic energies than you would at a lower temperature. But look, more importantly, what you're probably going to have to get out of a curve like this is what happens to the fraction of molecules that now have enough energy to react. So at the lower temperature, the blue curve, this is the fraction of molecules that can react, or the area represents molecules that react. And when you raise the temperature, so when you look at the red curve in comparison, the number of molecules or fraction of molecules that can react now is all of this. So you have, at a higher temperature, you have increased, as you increase temperature, you've increased the fraction of molecules that have enough energy to react. So again, please make notice of how to interpret and explain this type of graph. I introduced the Arrhenius equation a few slides ago. The form of the Arrhenius equation that is more commonly used, easier to use in the lab, is this one. So if you remember your logarithms at all, you can see how you get to the first form to the second form. And it's got an e, natural e in there, so we're going to use natural log to get rid of that e. Okay, so on the left side we have natural log of the rate constant. When you multiply two things together, when you're working with logs, you can separate them. So it would be log of A, for that A, plus, okay, so when you multiply two things, they end up being plus in the log, plus log of e to the minus EA over RT. Okay, so the log and e negate each other, and you end up with this form. So that's in the form of a line again, which chemists tend to like to do, don't they? And so you think of a form for a line, y equals mx plus b. And so you would plot natural log of the rate constant on the y-axis. And you would plot 1 over temperature in Kelvin on the x-axis. And your slope would be what? There. Okay, minus activation energy divided by the rate constant R. So let me show you, because this is very simple to do, but I've seen lots of students mess it up. The slope is not equal to activation energy, okay? So you have to do simple little algebra to get the activation energy. The slope, these lines have a negative slope, all of them. So let's just say that I'm going to make up a slope here, that I got a slope that was equal to point negative, they're all going to be negative, 0.0055. Okay? So how do you get activation from that? Activation energy. Well, what do we say slope is equal to? So let's just plug this in for slope. So that means that minus activation energy divided by the rate constant equals what I said the slope was, 0.0055. Now, what are we trying to get? We're trying to get activation energy, so you have to get it by itself. So minus activation energy, we're going to multiply both sides by R, right? So minus activation energy equals minus 0.0055 times R. Now you're going to want to use the 8.314 joules R value, okay, to get the proper units for energy. All right, so now we have a negative on both sides, which is typically what's going to happen, so they just negate each other, right? So then activation energy is 0.0055 times 8.314, and your units that you're going to get from this is joules. All right, so sometimes you will see people, they'll take the R value and they would rather have the activation energy in kilojoules. Usually that happens when you have a very large energy value. If you put it in kilojoules, it isn't so cumbersome to write down. So just so you don't get thrown off. So that's joules per mole Kelvin. If that were in kilojoules, if the answer asked you to put in kilojoules, it would be, remember there are 1,000 joules per kilojoule. So you would do your, okay, there are 1,000 joules per 1 kilojoule to cancel your joules out. So it's like dividing by 1,000, right? So 0.008314 kilojoules per mole Kelvin. Okay. So the last slide is a typical type of problem you might be asked, where you're given a graph and asked what the activation energy is. So you would simply find the slope of the graph, right? And then you would multiply it by negative R to get activation energy. There is another form of the Arrhenius equation that is commonly used. It's called the two-point Arrhenius equation. And in this one, you don't need a graph. You simply need two different temperatures and one of the rate constants for one of the temperature, and then you can solve for the other rate constant. So we've had a few other equations similar to this. You just have to be careful. Temperature's got to be in Kelvin. Just be real careful with the math. So here's an example. The rate of reaction doubles when the temperature is changed from 25 degrees Celsius to 36.2. I don't know if you remember the rule of thumb I gave you in the beginning of the chapter, but in general, for every 10-degree increase in temperature, our reaction rate approximately doubles. It's just a good rule of thumb. So calculate activation energy. So anytime you see activation energy in a problem, you are definitely going to need the Arrhenius equation. And so we've seen 3 different forms of the Arrhenius equation now, right? So you've got to decide which one to use. And it's not a graph, so we don't need the linear relationship. It gives us 2 temperatures. So that tells us we need the 2-point Arrhenius. There are a number of slightly different versions of the Arrhenius 2-point equation in a similar fashion that we saw when we were calculating energy difference between Bohr energy levels using that equation, and we also saw it in the Clausius-Clapeyron. So I want to show you a couple so that you don't get confused and think that one of them is wrong. So I'll show you for comparison. And by whether or not you have a negative sign in front of activation energy determines the order which the temperatures, the 1 over temperatures, are in the parentheses. Okay, so another equivalent version, they're both perfectly fine. So, and there's more than these too, but just to give you an idea of what I'm talking about. So in this version, let's say you don't want the negative here, right? So, but then you're going to have to change the orders of the temperatures, and either one you will get the correct answer. But be very careful of the formula that you use, and you don't accidentally drop a negative if it should be there, as well as the ordering of the temperatures. So let's plug in what we know. So I'm going to call K2 the faster one. Okay, the larger value. And I've got it on top in this. So I'm going to say natural log of, okay, I don't know the exact rate constants, but I know the ratio of the 2 of them is 2 to 1. So now I have to be careful that this temperature, I'm going to use this top equation just because it's there first, but the temperature that goes with this faster rate constant comes first. Okay, so equals minus activation energy over 8.314, and I'm out of room, so I'm going to go down here. Then the larger temperature goes first, and temperature has to be in Kelvin. So 36.2, I'm going to add to that 273.15 to find out the temperature in Kelvin, and it's 309.35. Okay, so again, I'm using the equation here. Minus 1 over the lower temperature, which is 25 degrees Celsius, so that is 298. And so now it's a matter of simplifying it. All right, so we have a little bit more room now. So let's go ahead and plug these values in and see what we have. So I've done natural log of 2 enough to know that it's 0.693. Simplifying further, I just calculated these to show my work and combined them. And I multiplied both sides by 8.314. I'm just trying to get activation energy by itself. Okay, so now all I need to get activation energy is to divide both sides by negative 0.000123. The negatives are going to cancel. And there we go. And doing that right now. And so activation energy is 46,852 joules. We could convert that to kilojoules, right? So just get yourself familiar with doing that because that happens a lot. And that would be 47 kilojoules. Well, it looks like we probably need another sig fig, right? So probably 46.9. And that is it. And finally, besides temperature, the other thing that can easily speed up a reaction is a catalyst. A catalyst is something that increases the rate of reaction, but it does not get consumed. So if a chemist is lucky, they'll be able to recover their catalyst at the end of a reaction and use it over and over and over. A catalyst speeds up the reaction by lowering the activation energy. How does it do that? It provides a new pathway. So uncatalyzed reaction would have an activation energy that large, and when you catalyzed it, much smaller activation energy, and therefore more likely, more reactants will have the energy required to make it over that activation energy hill. There are two types of catalysts that you should just be familiar with, just vocabulary. Homogeneous is the catalyst and the reaction are in the same phase. And so you just stir them together and you wouldn't be able to see the catalyst with air. Heterogeneous catalyst is in a different phase. So quite often you'll have, like activated carbon is a good catalyst. And it's just a black solid that doesn't dissolve in pretty much anything, but it has large surface area and will serve to kind of attract reactant molecules to its surface so they end up closer to other reactant molecules. In any case, heterogeneous catalyst means they're in a completely different phase. They don't dissolve or anything. And that is it. There is one more lecture from chapter 13, and it's about reaction mechanisms, the exact pathways reactants take to get to products.